Today we have Quoc V from Stanford University. He's going to tell us about his work on deep learning. And he's a student of Andring, and he'll be graduating in a year, hopefully. And this is a work he's been collaborating with people at Google. So, Quoc.
Okay, thank you. So I'm happy to be here to present some exciting progress in scaling up deep learning. Can everybody hear me, or should I shout louder? So, okay, so in the past few years, we have succeeded in developing algorithms that can learn feature representations from data. However, this algorithm turns out to be quite expensive. They're slow to train, and therefore we have to apply to small problems. Together with Google colleagues, we succeeded in making several breakthroughs in terms of scaling up these algorithms. And in particular, we are able to use thousands of machines to train these algorithms. And the results are very remarkable. And in particular, the feature representations that we use machine to learn seem to outperform a lot of human engineered features. So I'm going to share with you what algorithm we use and how we scale up these algorithms, and some of the key results. So this is the work that I've working at Google and Stanford. So why do we want to learn feature representations? So why does this matter? So, so here I show you an example of a very simplified case of object recognition. Here I have an image that has a face, and my task is to recognize whether whether there's a face in the image or not. Well, a standard procedure that one could do is to take some feature extraction methods. For example, you run some edge detection. In this case, as I said again, it's very oversimplified, but you run some edge detection and get the features. And then given the feature representation, which are the edges in the image, you run some classifier. So for example, SVMs, logistic regression, etc. Of course, there are a lot of other stages, but the two key stages in object recognition, for example, are feature extraction and classifier. And this is also common in a lot of other fields as well, not only in object recognition, but also in speech recognition, for example, or in a lot of domains in NLPs. Well, if you perform some analysis of this pipeline, for example, and I think some of you in the audience probably seen this, but let's say you take machine learning has succeeded in developing very good classifier throughout the years. So if you take the classifier and maybe you change the classifier from SVMs, for example, to logistic regression, right? Then performance might drop 1 or 2%. If you change some other classifier, it might change a little bit, not much. But if you change the feature methods here, then the performance certainly changed a lot. So for example, if I take instead of using the raw pixel representation, if I use the edge features, it works better. And if instead of using the raw pixel representations, if I use shift and hop features, they work better. And it turns out that this component, feature extraction here, is a key component in a lot of tasks in pattern recognition, in speech recognition, in NLPs as well. Well, so let's see what people use in their feature extraction. So it turns out a lot of these methods use something I call handcrafted features. So features that are engineered or built by human experts. For example, in computer vision, you probably know the shift or hop features, or the sub feature. And in speech recognition, you might know MFCC or spectrogram. And it's interesting that in a lot of these domains, it's really common to use these features. And for example, if you submit a paper to speech recognition, for example, and if you don't use MFCC and spectrogram, your paper might get rejected, for example. So it's very common to use these features. And the problem with these features, there are two problems with these features. So the first problem is that they don't generalize. So if you have a method that extracts features from images, then you might not be able to use it for text, for example. Right? So that's the problem. So if you want to, now you're interested in another domain, you have to sit down and engineer these features again. The second problem is that these features seem to take a long time to develop. So for example, the shift and halt feature that we may know in computer vision takes years and decades for people to develop. And then after many years of research in computer vision, for example, they're quite successful. But we still seem to be still stuck at shift and halt. And the reason is that the process of coming up with these features are very laborious and complicated. That even though we know that there are rooms for improvements, it's so complicated that we don't know how to do it yet. So, so a few years ago when I started working on machine learning, right, I talked to a lot of people and I asked them what are the most important and interesting problems for me to work on in order to solve big problems in AI. And a friend of mine, and together we did this analysis and trying to read through the literature, and we seem to come up with a conclusion that it would be nice to actually find a way to get machines in designing the features for us. So instead of for us to invent the features, we get machines to invent the features. And this ambitious dream turns out to be to reflect a good insight. And recently in machine learning, there's an emergent field to design feature representations, and the field is called unsupervised feature learning. And it's also built on the concept of deep learning. I'm going to elaborate these ideas later. And so at Stanford, we actually at the frontier of this kind of research. And we developed a couple of algorithms that are quite successful. But among the algorithms that are most successful, we have the RICA algorithm, the Reconstruction Ica algorithm that we used, and also successfully use it for scaling up. And I'm going to talk about the Reconstruction Ica algorithm. So one key problem with a lot of these algorithms is that they're quite slow, as I said earlier. And we typically apply them to small problems. And when we apply to small problems, we don't know whether the promises that we've seen when we in the small problems can still hold for bigger problems. And we don't know that. And right now, there are two questions for this field: is how to scale these algorithms up, and the second question is whether the potential that we see in the small problems can generalize to bigger problems. And in this talk, I'm gonna show you evidence for some answer for those questions. So I mentioned earlier that deep learning and unsupervised learning cannot use a lot of data. We can only apply to small problems. So what is the problem? So not being able to use a large amount of data can be a disadvantage, because right now and in the future, there will be a lot of data. And I live in the Bay Area, Silicon Valley, and as you know, there's a lot of data. There's a lot of tech companies, and data seem to matter a lot. So for example, every day you have 200 million Facebook images uploaded. Right? That's a lot of data, and we better make use of it. And right now, deep learning and unsupervised learning, because they're so expensive, we cannot use it. But my personal belief is that having a lot of data will lead us to solving bigger problems in AI. And I think one thing that's missing in a lot of things like speech recognition or object recognition is that right now we don't use much data yet. And I think it would be good for us to use it. Okay, so this is the outline of the rest of the talk. So I already motivated the question of engineering features. I motivated the question of using large amount of data. Now I'm going to talk about the Reconstruction Ica, which is the algorithm that we use to invent features, to learn features from data. And because this approach of learning feature representation is very is interesting because it is not domain specific. You can use the feature representation, you can use the method to learn features from a lot of domains. So in particular, I will show evidence that it can learn features from videos and then cancer images, domains that it's very hard for us to invent features. Then I will talk about some ideas to scale up these methods, and then I will show some interesting results at the end. Okay, so what is the Reconstruction Ica algorithm? Well, the Reconstruction Ica algorithm is built on another algorithm called topographic independent component analysis. So the idea is as follows. You learn some features, and then you map from the features into a topography. So here I show a 2D topography. And then it will learn some coherent representation such that if you combine the features in a local area of the topography, you get some invariances. So let's say here I apply to images, and then it will invent from some edge detectors. And then the edge detector in the local area of the topography are sort of coherent, such that if I combine the responses of the feature in that area, I might get some rotation invariance, for example. So here's the example is from images, but it's not restricted to images. So how does it work? Well, okay, so let's start with some data x. Right? So here's I have a little image x. It's represented by a vector of maybe 100 dimensions, for example. Now, I take a 3x3 region inside the grid. Okay, so and I end up with 9 features, W1 to W9. Every feature has the same dimension with my data. Okay, so I have 9 features, and then I take the dot product of my features with my data. So that's a scalar, and now I end up with 9 scalar. Okay, and now I sum up. I take the square of all the scalars, and then I sum them up, and then I end up with 1 feature. So this is one. The J is indexing the feature in the map. Okay, so let's say the map that I have has 100 places. Then J will go from 1 to 100. Okay, and for each location of J, I have a feature, and the feature is indexed by my data xi, okay, and some location in the map J. Okay, now the question is that, okay, so here I cheated a little bit because I show that the edges are coherent. So where does the edges come from, right? So that's the question of learning. So in learning, what we do is we want to maximize the sparseness of the features. So in a more mathematical term, you want to minimize the activation of the features. So you want the sum of all j across your data and across the map. You sum it up all across the map, across the data, the feature h, right? And then you want it to be small. Right? And if you want it to be small, one answer is to set w to be 0, right? And then you end up with a 0 value. Now, and then 0 is not a good feature for us. Now, to prevent that from happening, what you do is you say that the features are different from each other, and they have norm-bounded. So in particular, if I say my w is a stack of all w's in this map, okay? So I stack all my w's in this map. Every row is every row is my one set of feature. Then I want my w to be orthogonal to each other, right? Now, after you have this, you set your topographic map to be random, and then you optimize this constraint. You compute your h, compute the gradient, and then you project the gradient at every step. You solve w transpose to be identity, and that's it. So, okay, and then after you learn that, here I apply to color images. Then it will organize the random filters until you have some coherent representation like this. such that if I combine the features in a local area of the topography, I will end up some invariances. So for example, I can learn some rotation invariance, translation scale invariance, and scale translation invariance. And the reason why invariances are important is that if you know that if you take a picture of an image, right, and if the object is translated, if you take a picture of a car, if the car is translated, then you want the feature representation to be stable. So that's the same image of the car. And same with rotation invariance and same with scale invariance. If the car is bigger, you want the feature to be able to capture that.
Sorry, how do we know that this is scale invariance?
Okay, sure.
Scale invariance?
Sure. So if I have a filter that is lower frequency, right, it detects a bigger edge, right, and if it combined with an edge that is very small, right, so if you combine it, you can achieve a concept that can detect a big edge in the image and also a small edge in the image. So here is able, right, it's able to detect a big edge in the image, and here is able to detect a small edge in the image, and then by combining them, you can achieve some invariances. So you will say that if you give me an image, if whether it's small or big edge, I will be able to detect it still. Right? I want to explain that concept right now. Okay, so so images in 2D are complicated. So I draw an image in 1D. Okay, so let's say I have two images, image number 1 and image number 2. Image number 1 that has an edge at location 1, and in image 2 I have an edge at location 2. Okay, they're translated from each other. Right? If I use filter number 1, feature number 1, right, then feature number 1 can tell me whether there's an edge at location 1 or not. But it cannot tell me whether there's an edge at location 2 or not. Right? It doesn't do that unless you use convolution or something. But let's say we don't use convolution. We just say, let's say I have F1, then I can tell that there's an edge at location 1. But I can't tell whether there's an edge at location 2 or not. Vice versa, if I want to detect an edge at location 2, then I invent a feature that recognizes an edge at location 2, then it failed to recognize whether there's an edge at location 1 or not. But so each of the feature can't capture the concept of, I don't care whether I don't care whether the edge is translated or not, but I care if there is an edge in the image or not. Then one of the features fail. But if you combine the two features, then you can achieve that. So here's how I combine it. I take F1 and take the dot product with the image, right? And then take F2, take the dot product with the image. Then you end up with two values. And then I sum up the two values. I square them and take the square root. And then what happens is that for image number 1, the result is 1. And for image number 2, the result is also 1. So that means the value of the feature, the way that I combine the feature here, is independent of the location in the image. Right? So of course, like y is square and y is square root is a little bit more complicated because it's actually more relevant to the 2D image and more relevant to the other invariances that you can find images too. But the concept here, the idea of combining multiple features and build up a hierarchy holds the same.
Why do you decide the filters should order in a 2D grade instead of 1D or 3D?
Okay. So normally people, so it's an input in the algorithm. You say I want to learn 1D topography or 2D. So it's independent of that. But I explain in 2D because this is one is that it's actually relevant to the concept of what happens in the V1, that they discover that in V1 of the brain is actually has a topography. The second idea is that because in the literature, people often describe that way.
Did you find 2D to be best?
For images, 2D is better, and it's actually also relevant to what I will talk about in the next section when I talk about local receptive fields and so on. But it usually works better. Yeah. Okay, so I've been talking about TICA, the algorithm, topographic independent component analysis. It turns out that topographic independent component analysis works really well, but it has one weakness, that it never be able to scale. So the problem is I highlighted here a red box. So in order to train this algorithm, we use something called the projected gradient descent. And the projected gradient descent works as follows. You compute the gradient, right? You compute the updates of the algorithm, of the parameter, and then you project your parameter into the constraint. Now, the constraint here is projected using something called the eigenvector problem. So every step you have to solve an eigenvector solution, which is very slow, right? N-cube type of algorithm. You don't want to use that. So at Stanford, we try a lot, and then we finally figure out a way to actually scale this algorithm. And the way is actually turns out to be quite simple and described in this paper here, our 2001. The idea is that you turn the orthogonal constraint to a reconstruction constraint. So the reconstruction constraints say this. I want to find my W's such that W times X, and then take the W and transpose of that, then would be similar to my X. So I want to minimize that objective in addition to the sparsity objective. Right? So it's a combination. It's going to be a soft constraint instead of a hard constraint. And in our next paper, we prove a bunch of a sequence of lemmas to drive the connection between this algorithm and that algorithm. It turns out that they are equivalent. I show the equivalence later. And the equivalence is also interesting. It's actually draw a connection between a lot of popular algorithms that we thought of actually disconnected inside deep learning. We used to think that these algorithms are not related. A lot of people invented features algorithms, but they thought are unrelated. But it turns out by reading this paper, you can see that this algorithm turns out to be related, and by the lemmas. So it actually draws a connection between sparse coding, something that developed in the 1990s. RBMs developed in 2006, ICA in the early 2000s, and auto encoders probably long time ago, maybe early 1990s. And the algorithm we have also let us build a hierarchy of features as well. So now I want to focus and talk about what is the connection here. So let's say I take the algorithm that we have here, the Reconstruction Ica algorithm, and I will focus on the red box, which is the soft constraint that we have. Okay, so I will focus on the red box, and then I will prove that under some assumption with the data that we can enforce so data sphere. So you do some local contrast normalization in the data. You can prove that that constraint right there is equivalent to the constraint that I draw here. So this is called column orthogonalization. Right? And via some mathematical things, you can prove that it's actually equivalent to column row orthogonalization, and then by ramping up your lambda, you can achieve the harder constraint. So you can find the proof in this paper here. Quite technical though, and then after having proved the equivalence, we can see that the harder constraint is actually turns out to be the soft constraint right here. Okay, so why do we use Ica even though it actually has a lot of connection between these algorithms? So it turns out that So we at Stanford, we work a lot of these algorithms, and we discover that some of these algorithms have different weaknesses. So for example, the sparse coding algorithm, I'm not sure you're familiar, but it's one of the most famous algorithms that can learn edge detector from unlabeled data. It turns out that algorithm has only one parameter, so it's very simple to train. Right? It has only one hyperparameter, so you tweak a little bit and you get what you want. But it doesn't learn invariant features, and it's very slow. So autoencoders, on the other hand, are very good engineering solutions. So they're very, very fast, but they have a lot of parameters. So it's very difficult to train. By parameters, I mean hyperparameters that we tweak. And it doesn't always learn invariant features. So TICA, I focus on in the earlier section of the talk, is very fast. It's not very fast, but it's simple to train, and it can learn invariant features. Reconstruction Ica is a great combination of these two algorithms. So it has a strength of TICA that is actually has very few hyperparameters. Actually, it has one, and it can learn invariant features. But it's also very fast because we use a harder constraint like an eigenvector solution to a softer constraint, and it actually works. It actually can be trained a lot faster. Okay, so far I talked about the reconstruction ICA algorithm, and I think that the only take-home message is that it's actually we use reconstruction cost instead of orthogonalization, so it can scale, and it can learn invariant features. So that's very simple. Before I move on and scale this algorithm up even further, I want to show some example applications of this algorithm. Right? So it turns out what I've just showed you is an algorithm that can learn features from data, and it can learn from any data you want, not just images. Right? So in particular, in our CVPR 2011, we show that the feature learning method can learn features from videos, and we actually want to apply this for action recognition in videos. Right? So for example, we want to detect whether that's an action of getting out of the car, right? And we want to learn features for that, for eating and so on. And so the state-of-the-art features in this domain is to use SIFT or Hawk features, the feature that are engineered feature that I described earlier, and then they also take that and extend in 3D, for example. Right? And what we do is we sample blocks from these videos, and then we learn features from them. And as a sanity check, we visualize the features, and we want to know what kind of features it learns in the first layer of the network. Right? So, and then what I show here is a concept that it learned in the first layer, and it turns out that it's actually learned some edge detection filters in 3D, which is as a sanity check. Is actually does what we could have invented, right? Because some of the SIFT and Hawk features that people invented is based on an edge detection in 3D, and it seems the algorithm is able to capture that. But higher layer in the network is harder to visualize. But I'm gonna show some results later. Okay, so we took the features that we learned from data and then compare with a lot of engineered features. So what we see here is the results of our benchmark compared to computer vision in 4 most famous activity recognition datasets: KTH, Hollywood, UCF, and YouTube. So people have worked on this for many years. For example, the KTH dataset has been around for like, I don't know, maybe 10 years or so, maybe less, I don't know. But in this, I show accuracy, so higher is better. And what's surprising is that the learned feature representation that we have turns out to outperform a wide variety of features that people have engineered. So for example, Hawk, Hoff, and so on, we outperform all of them. And not only on one dataset, we actually outperform on 4 datasets. And these are the most famous ones that people care about. And so one computer vision expert actually came to me and told me this observation as well. He said that people have tried this and using hand engineered features, but what they usually observe is that hand engineered features only work for one dataset. So for example, in the Hollywood 2 dataset, Hawk feature works best. But in UCF, something else works better, for example, Hawk 3D. So he said that we never seen that one feature seems to do best for all datasets. And this is the first time that he actually has seen this. So that's very interesting. And that the learned features seem to be able to capture the right statistics from the data. Another favorite example that I have is in the domain of inventing features for biomedical images. So in particular, I have some collaborators in University of San Francisco, UC Davis, and Berkeley. And the task that they care about is given some MRI images from the cells. They want to invent features to detect whether there are cancer or not in the cells, and whether what type of cancer that is. And I asked a lot of my friends to invent features for this domain, and a lot of them actually gave up because we seem to do well for vision because we have a good intuition for that. But for this domain that is come out of nowhere, our intuition about inventing features, like our usual intuition, breaks down. And the best they come up with was some edge detection, some color histogram, and so on. So it's not very good. And indeed, the people that my collaborators actually used those features. And here I show a combination of many features. So the green bar is the accuracy using a combination of all these engineered features, right, together. And the Ica algorithm that we have that learn features from data turns out to work very well. Yes.
So did you try PCA for single value compensation?
Yeah, we do.
How the results?
Oh, you mean compared to Ica?
Yeah.
It's actually a lot worse. So the Ica algorithm, yeah.
From my curiosity, why did you not present it in the full picture?
Oh, I see. Yeah, because it doesn't work very well, so we didn't
No, at
present
least
it.
we would like to know how that compared to human engineered features.
Right. Okay. Sure.
Do you think that PCA will work a lot better than those
Hand engineered feature, it is worse than hand engineered features. Yeah.
Really?
Yeah.
Wow, I learned here.
I can forward you the paper afterwards.
No, but
Okay.
if you can explain what's make that a huge difference.
Okay. Sure. So PCA is a dimensional reduction method, right? So PCA is usually an orthogonal transform of your data. Is a linear transform of your data, right? So a linear transform of the data usually, at best, it can what it can achieve is some sort of dimensional reduction and prevent overfitting. Right. So in a lot of our cases, they don't work very well. So, and in particular, the Ica algorithm that we have is a non-linear transform of the data, and the non-linear transform seem to work a lot better for this task. So that's what we observe. But yeah, we can take this offline. Yeah. Okay.
For the images and for this, the raw input is just the intensity.
Yeah. So the data to the algorithms are like intensity data. Yeah. Okay. So far so good, right? I already showed you some examples of these algorithms working really well for tasks that is very difficult to hand engineer features. Now I'm going to take these algorithms, this algorithm, I'm going to scale it up further. Right? And why do I need to scale up? So what happens in a lot of deep learning literature right now is sort of somewhat a little embarrassing, is that we have a very big task. I represented here some big data, right? And then because of the computational challenge with deep learning and unsupervised feature learning, what we do, we take that and then we scale it down. Either we downsample the images or we throw away examples and so on. But as you can see, there's so much that we can learn from this picture rather than about that little picture over there, right? So it seems to be very obvious that we should invent methods to work on this. The problem is actually the computational challenge associated with it. The other observation that we have, actually my colleague at Stanford observed this. So you take a lot of feature learning methods, not only the Ica algorithm, but we take k-means, RBMs, autoencoder, and then we increase the number of features that it learns. So this x-axis is the number of features. And then he plot the accuracy on the validation set. It turns out that the more features we have, the better it's going to perform. So it seems that we want to work on bigger images and we want to make the representations a lot bigger. So at Stanford, we worked really hard on this, right? So this is one of the main agenda that we have, to scale up feature learning methods. We tried so many years, but we finally succeeded. So the success is to come to Google and ask for 1,000 machines. No, actually, it's not that. So it turns out that using 1,000 machines alone is not enough. And we actually made a lot of changes in the algorithms, and those turns out to make use of 1,000 machines very well. So where do we start? So the first step is we do some analysis of the feature that we learn. And so here I show the visualization of the feature in the first layer, right? Higher layer is very difficult to visualize, so I can't do it. But let's say visualize the first layer. Turns out even though we ask the algorithm to see the entire image, what happens is that a lot of features turn out to be localized. So even though here I learn feature for 20 by 20 pixels, the feature turned out to be quite small. It's a little area in the image. Of course, there are like non-localized features in here, but there's a small fraction of it. Right? So one good approximation is we go to the algorithm and then we enforce that constraint directly. So one way to enforce is this. So we take the Ica algorithm that I talked earlier, right? And then we say that so here every feature connects to the entire image. But then we say, okay, I'm going to trim down the weights. So I'm saying the feature number 1 can only see a small area of the image. Feature number 2 can see a small area of the image, and etc. And then we enforce this constraint everywhere in the network. Okay? Now after having the explicit constraint in the image, right? Now in the network, what we can do, we can carve the network vertically. So we divided the computations such that the feature computation for those 2 nodes can go to machine number 1. The feature computation for these 3 nodes in the middle go to machine number 2. And the feature computation for these will go to machine number 3, and etc. So it's a very simple but very effective way to actually parallelize the training of these models. Right? So of course, there will be some communication across the machines a little bit. But we can design the batch size and so on so that the communication is very small to the computation of the features. And this is one of the first steps that seem to be very successful in parallelizing this network. Well, that idea can let us parallels to maybe 100 machines, but 100 is very small. We want to use a lot more than that. Right? And we want to go to 1,000 machines because with a factor of 1,000, we might be able to use big images. So when we use 1,000 machines, there's a challenge. So the challenge is that when you use 1,000 machines, the chance that one machine will die during your computation is very high. Right? once in a while, one machine will fail the disk or fail the RAM, etc. Many problems. And even we run this in a shared cluster, so people have also run jobs in our cluster too. So maybe some machine will be preempted, right? So, and everybody has to wait for that guy. So it's very slow. Huh? So we want to have a way to parallelize better. So we finally found a way to do that. So here's the idea. It's actually going to appear in our paper 2000 ICML coming up. So the idea is this. So you take your data, right? Million examples. You divide it into, let's say, 4 chunks, right? And each chunk will train your stochastic gradient. So your stochastic gradient descent will be trained on each of the chunks, right? And we use 100 machines to train it. So they train independently. Now we have something called a parameter server that keep the latest stage of the parameters, right? So this is the entire parameters that we have. And then every once in a while, the server will inform one of its slaves the current state of the parameter. So it will send the parameter to each of the slaves and say, okay, this is the new slave. And the slave graph the parameter, right, asynchronously though, and then compute the gradient and send the gradient back to the parameter server. So when I say asynchronous, what do I mean? What I mean is that all these guys can be run out of sync, right? They can be run out of sync entirely. So for example, the parameter server doesn't care where the gradient it gets from. It just say that if it receives a gradient, it will make an update to the parameter. Now that is very resilient to failure, because let's say one of the guys will fail, right? During training, one guy just go down. Then everybody can proceed, right? Everybody can keep training, and then make update to the gradient, to the parameter, and so on. But if anybody go down, if this go down and then go back up again, he will contribute to the entire training, and it still works fine. There are some formal analysis of this algorithm in a linear and very simple model. But this is the first time that somebody have observed that this is the first time that we have observed that this mechanism of training turns out to work very well for very complex and non-linear model too. Question?
So I have a question. Do you parallelize across the data or the parameter space? Like,
okay.
What is this
okay.
chunk represent?
So this is parallelized across data. And each chunk here will be parameterized across, it will be parallelized across model.
So each chunk sees all parameters, but only fits it on a small portion of the data.
Yeah, that's right. Each chunk.
Within the chunk, you parallelize across
the parameter, like the first idea, right? Okay. So each chunk will run the first idea. So carve the parameter vertically, right? And then it will compute the gradient, send it to the parameter server, and then the parameter server grab the parameter and then make the update. It doesn't care where does it come from, right? So everybody can run out of sync. So nobody. So this contrast to the very conventional way of training is that you have one guy. The server has to wait for everybody to send the gradient in order to make the update. But this is out of sync, right? Okay. So I want to move a little bit faster, and I say that the two main ideas that we have is local connectivity and asynchronous HDD. And these ideas turn out to work very well. They're simple but very effective. Of course, we actually try, this is a big software engineering project. We did a lot of things as well. Some of them small but also effective, but I can take this offline and talk about it if you're interested. Okay. So in the problem that I tried, we trained on million of images, so 10 million of 200 by 200 images. So we take the algorithms that we have, train on 1,000 machines, 10 million images, right? And the number of parameters is 1 billion parameters. So in terms of scale, this is 100 times bigger than anybody has ever tried in deep learning, and probably in somewhere in computer vision too. And the algorithm is as follows. So you take the image, right, and then train a sequence of bigger algorithm that I talked earlier, right? And then we're gonna train on 2,000 machines, and these machines have 8 cores in general. So we have 16,000 cores, right? And then we train it for 1 week. So the number of parameters is 100 times larger than anyone you have tried. But although it's quite big, it's actually small compared to what happens in the brain. Okay, so after the training, what we have to do analysis to understand what's going on, what we've learned, right? So we take the neurons at the top layer, one neuron at a time, and then we give a lot of images to it. So this algorithm is trained with unlabeled data, okay? It's entirely unlabeled. We take the neuron at the top, and then we give a lot of images to that neuron, to the input to the network, and then we see what neuron, what images it like to see the most, okay? And surprisingly, there's one feature, there's one neuron that is actually very sensitive to faces, okay? So when we visualize the top 100 images that it likes to see, that's how all faces. Now one of them is actually not faces, but it's actually very like looks like a face. And we also perform. We say, oh, maybe it may be lucky. So what we do, we hold the value of the neuron, and then we say perform optimization from random with respect to the image. So we do gradient descent on the image, right? And then we see one, and then we visualize what it's like to see. It turns out that it's also like to see a face. And then when we do more analysis, we give a random instructions to the network, and then we give faces images to the neuron, and it turns out that the histogram is very distinctive. So if you have the histogram like this, right, then what we can do, we say if the value of the feature is bigger than some values, then we can be confident of that's a face, and otherwise we're less confident whether that's a face. And we performed some analysis, and we found that it's actually quite invariant to a lot of transformations in the image. Okay, there's another feature that quite interesting. Is actually it's also invariant to it's actually sensitive to the concept of cat faces. I'm not sure that you can see from this picture, but it's actually after optimization, it looks like a face with the ears and so on. Okay.
Question: where did the images? How did you collect the images, or?
So we use a lot of images from ImageNet.
ImageNet.
Yeah. Okay. So the histogram. Okay. Okay. So there's a lot of other features as well. And for example, we have dotted features, diagonal edges, circular detectors, and I want to point out that there's a lot of invariances going on. Right? For example, this circular is actually out of length, and it's also the features seem to be able to capture that. And also it groups pink and purple flowers together in one feature. So, and then there's another feature that is insensitive to the concept of yellow flower on top of green background. Some bird detectors. I have a neuron, interesting neuron that is actually insensitive to the concept of zebra. One neuron is sensitive to the concept of keyboards, bottles, and pizza. Okay, now we have all these great feature representations, right? From unlabeled data only. Let's make use of it. So what I'm going to do is I'm going to take the features and train some classifier to classify 16 million images, okay? 20,000 categories, right? So the number of categories is basically equal to the number of images that I tried when I was a grad student at Stanford. So, but 20,000, when people say 20,000 categories, what's that, right? It doesn't seem very impressive. So let me tell you why 20,000 is a lot of categories. So here I show a very, very small section in the 20,000 categories, and this is a lot of kind of species inside the data set. And one thing that we asked to classify is, for example, stingray versus manta ray, right? And so what's that? Okay, so manta ray and stingray, right? They're visually quite similar. So this data set is quite challenging. It's probably one of the largest scale and probably one of the most challenging data sets in computer vision right now, if not the most challenging. Okay. Okay. So because it's very challenging, random guess doesn't get you very far. So it will give you 0.5%. If you guess randomly what category is it from, like that. Okay. Computer vision with a lot of engineer effort seems to work pretty well. It moved from that number to 9.5%. So that's pretty good. Okay. So this is a combination of Hawk, Sith, pyramid, and so on. So lots of complicated math. Okay, so when I saw this, I said, wow, that's remarkable that you 20,000 categories and we move up to 10%. So let me try my feature learning method. And a lot of my friends said that, actually, I've been educated to use shift and Hawk features in my life, right? What does it mean that I should learn feature from raw pixels and then use it to classify? I think you will fail. That's what my friend told me. And when we applied it, we got it to 16%. And so if that doesn't sound impressive, okay. So in ImageNet has several versions. Right? So 2009, we also way better than state of the art. Now that doesn't seem impressive because 16% seems small, right? It seems like error rather than accuracy. Right? So what we do is we go one level up, right? We say instead of ImageNet is like a tree. It has here we classify the leaves, right? Now instead of saying classifying whether it's manta ray or stingray, which is challenging, we say whether that's a fish or not, or whether that's a car or not. We don't really care with a Toyota or is it Ferrari, right? If you do that, right, we have 50%. Yes.
So are the categories are very highly skewed?
No, the one unfortunate thing about this data set is that the categories are well balanced. So it's not a natural statistic. So each category is well represented inside the data set. Yes.
The question: what method do people use to train like a classifier with whatever number of features that you've learned? So what is the you've learned features? But what classifier do you use to?
My classifier?
Yeah. What
we use flat classifier, submax. That's it. But we have a. So we actually, that's a very interesting question, right? So right now in computer vision and in machine learning, people have used like the fact that there's a tree associated with the data set, right? And I think that's a good idea. We never have such great success with that. And we use brute force, flat classifier, one versus rest, or submax, and that seems to work well. That works for us. All the effort will go into prioritizing all these, classifiers to make it really fast. And that's all we do. And that seems to work very well.
Under certain conditions. So basically, if each image has only one category, probably.
That's right. Yeah, that's right. So that's a very, very good question. So here, every assumption, the assumption is sort of naive. So each category has only one. Each image has only one category. Of course, in real life, it's more different than that. Right? We're working on that challenge at Google right now. But for now, that's what we have. Okay. So in this talk, I went through the Ica algorithm that we use successfully for a lot of domains. One interesting result is that when we scale up this algorithm using thousands of machines and a lot of data, we seem to be able to discover very high level features. For example, faces, gaps, and so on. And the strength of the algorithm is actually not domain specific, so we can use it to apply to a lot of tasks that we were interested in. Okay, I want to talk briefly about this only, but this project seems to have already had success at Google already. But I will probably talk less about that. Okay, so if you're interested in this work, there's a coming up paper. This is my website, and the paper is going to be out in a week or so that describe all of these things, right? Not only the results on, so we also have results on speech recognition and text as well, but in this talk I'll mainly focus on vision. And in the paper there will be things like optimization and more detailed formal analysis. This work is actually built out of a series of papers that I wrote earlier, and it's actually made use of them. And this work is actually possible because of very, very smart engineers and researchers at Google that helped me with parallelizing the algorithms. That's all I have. Thank you.